Hi, this is Stephen Brower from Merritt Valley Community College. This is for CSIT 256, Computer Architecture and Assembly Language. This is accompanying Stallings Chapter 11. Part 1 of the map went through a 3 variable demo, and this here is going to be a 4 variable demo. And if you're looking at the logic table, the reason why initially it's empty is I just kind of want to remind how, if we're using the zeros and the ones, how easier it is to actually do the inputs. And so with a 4 variable input, if we treat it as like a 4-bit binary number, we can start off with 0, 0, 0, 0. Then for the next row, we add 1. So 0, 0, 0, 1. Next row, we add 1, 0, 0, 1, 0, and then 0, 0, 1, 1. So we keep adding 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0. I'm sorry for the chop in the video. I just had a notification that came up in the lower right-hand corner that I didn't think was appropriate to leave in the video itself. And so there's a little chop here. I do apologize. But if we're leaving off here, 0, 1, 1, 1, and then we add 1 to it, we hit 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0. Did I screw up? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. No, I just missed a row here. Okay. Plus 1, 1, 1, 1. 1. I got thrown off by that. So this should be our 16 rows. 1, 2, 3, 4, 5, 6, 7, 8. That was less counting again. 1. Okay, our 16 rows. And because I did it this way by constantly adding 1, I'm sure that these values are unique. When you use the F's and the T's, it's very easy to duplicate rows or miss rows or both. But by using this method, by always adding 1, we will come up with the unique set of values. Okay, doing short circuiting, anything and false is false. So anywhere that C is false, this will evaluate false. So I can just, in terms of short circuiting, go in and where the C is false, put that in. So here, if BE is true, well, those are both 0, 0, those are 0, BE is 0, BE. Here, B and E, they're both true, so those are true. And then we look at C, so those are true, these are true, these are true. Now again, you may have already looked ahead and figured out what the simplified one is, but we're just going through the process. So this is the truth table for this Boolean expression. A equals, now the BE here, these are what the Stallings shortcut is by not even showing the period between it. That's B and E, or C or F, and this whole expression here ended with C. Now, the Karnaugh map. So with 4 variables, we have 2 on one side, we have 2 the other. When we go row to row, we only want to change 1 bit. So from the first row to the second row, only the second bit changes. From the second row to the third row, only the first bit changes. And then from the third row to the fourth row, only the second bit changes. And then when we do a wrapping, this last row here to the first row, only the first bit changes. So the thing with the Karnaugh map, we got to make sure row to row, there's only 1 bit changing in terms of the inputs. Column to column, same thing. So the first column to the second column, only the second digit changes. The second column to the third column, only the first bit changes. And the third column to the fourth column, only the second bit changes. And the last column to the first column, there's only a 1-bit change. So then it's a matter of filling in this table from using the inputs. So BE00 and CF is 00. So BE, CF, it's 0. Then BE00, CF is 01. BE, so 0001, it's 0. The BE00, CF11, that's this one right here. And that's 1. And then BE00, CF10, that's this one here, and that's 1. So now the next row of the Karnaugh map, BE is 01, and CF is 00, that's this. So that goes here. And then for this one, 0101, 0101, that's this. We have the 0 here. So now this one, the 0111. Well, the 0111, that's this one here. That's the 1. And then the 0110, 0110, that's the 1. And then the 1 goes here. The next one, BE11, we're down here. So 1100 is 0. 1100 is 0. This one is 1101. 1101 is 0. Then we have 1111. 1111 is 1. And then the last one here, 1110. 1110 is 1. And so now our fourth row in the Karnaugh map, 1000, 1000, that's this. So we have a 0. And then here, 1001, 1001, that's 0. And then here, 1011, 1011, that's this, which is 1. And then our last one, 1010. So our 1010 is 1. And then we have here our 1. And so now that we have our Karnaugh map filled in, we can work on the grouping. And we want to do it as the largest power of 2. Well, I just covered 8 ones that are contiguous, and they have to be contiguous. So I have 8 ones that are contiguous, and so this becomes our mapping. And these are the only so these are the only ones that we have. This is our only mapping that we need within here. Okay, so this mapping here, well, it covers all rows. So that would mean B and E, those variables are not in the final function because this mapping is covering all rows. When we look at our columns, the F, the second one, sorry, I get this right. The F here is 1, the F here is 0, so both values of F are covered. So then what's left is the first bit, the 1 here, that would represent C as being true. So our reduced formula is A equals C. That's the reduced formula that we have, which if we now were to compare our C column to our final function, we see that it's the same. So in other words, it doesn't matter what the B, the E, and the F are in terms of inputs. All that really matters in terms of the end is what C is. And so that C is really defining this final function. Now for these two demos from part 1 and part 2, they simplified down to 1 letter. The architectural lab you're going to be working on does not simplify down to 1 letter, but these are just the demos that I did here. You want to make sure you're showing the mapping, the covering. So like this box I have here, you want to make sure you show that on the architectural lab as well. So again, for simplification, this is just one of many methods that are used for simplifying Boolean expressions. Using the postulates and the theorems, those can be applied to a function in order to reduce it. This right here is sort of like a brute force method. It works best with 4 variables. One of the other methods that the book covers is the Klein-McCluskey method, which can be used for more than 4 variables. So Karnaugh Map is really just for 3 or 4 variables. The Klein-McCluskey would be for 4. And the reason why I'm having us go through this, again, is just more in computer science. You're going to have to demonstrate that you can trace through an algorithm in order to perform some kind of a function. I know the demo that I just did here, it's a very simplified one, that it could have been done easily using another method, but we're just trying to go through the process of basically tracing an algorithm. Okay. I think that's it for Karnaugh maps.